Okay, so we don't have a quiz, but we have a problem set, and we will answer that next meeting, next week, next meeting again. So first is draw the predominant form of aspartic acid at its isoelectric point. I hope that you can see my screen, and then draw the sequential transition of glutamic acid as it passes from its fully protonated form to its deprotonated form as the page rises. Of course, when you draw the structure of glutamic acid, you start here, since it mentions, you start with the fully protonated form, both from the carboxylic and the amine group, and then the side chain, the protonated form side chain. And then number 3, it's a tetrapeptide abbreviated as DPKH, which amino acid is the N-terminal, which is the C. And if you can draw the structure much better. Number 4, draw the structure of the tripeptide made of threonine, arginine, and methionine. And there are different possibilities, but you can start with threonine. Number 5, use the 3-letter abbreviations to write the representation of the following peptide. Now let's move. Okay, so for today, we will be talking on the hierarchy of the protein structure. So there are different levels on the structure of the proteins. Number 1 is we have the primary structures. We have already mentioned on the sequence of the amino acid, amino acid residues, we start from the N-terminal end up to the C-terminal end. No, if we write the sequence of the amino acid from left to right, or if we write the amino acid sequence top down, top to bottom, then top will be the N-terminus and bottom will be the C-terminus. From the primary structure, we can actually, or the amino acid residues can actually assume a secondary structure that, depending on the forces of interaction that will occur between the amino acids, and that will give rise to the secondary structure. The secondary structure, it will give rise to a tertiary structure where you have the polypeptide chain units folded, and then much higher than the tertiary structure is the quaternary structure. So again, I have mentioned what would the sequence of the primary structure consist of. And the secondary structure, we'll be talking each of this primary structure. So there is what we call the special arrangement of atoms. In a protein, you call this one is a conformation. So the possible conformations of protein may include a structural state that can be achieved without breaking of covalent bonds. So for example, a change in conformation could occur by rotation about single bonds in the structure of the amino acids, okay? And of the numerous conformations that are theoretically possible in protein containing hundreds of the single bonds, one or more, a few generally predominate under biological conformation. So we have to remember, you know, like I can't next my slide. Okay, so we have to remember now that in the peptides of proteins, in the peptide residues, now we have the covalent bonds, and there is this portion in the peptide bond that can be rotated. You have the CC bond and this one is not shown here. The NC bond now can be rotated. It's only the C double bond O and CN cannot be rotated. So because of that possible rotation about the single bonds, the peptide bonds rather in the peptide structure of the protein, it's possible for this to be rotated, and that would actually lead to a different conformation of the proteins. Aside from that, there are possibilities of several types of interactions that would occur, not here, but we'll look at later on the side chains of the amino acids. So this in the primary structure, the CC, canine CC can be rotated, and the NC or CN, NC bonds from the peptide structure can be rotated. No, so and that would give rise to different conformations of the protein. Secondly, we have the side chains here. If they are polar, they can actually also assume weak forces of interaction, such as hydrogen bonding. So there you can have the what you call as conformation of the atoms in the protein. So the need for multiple, with that particular conformations of proteins, so there are changes that would occur. And under biological conditions, that particular rotation that bonds in the proteins, the sequence of the amino acids, will actually assume a stable conformation under biological conditions. So we will be looking at that later on what are the most stable conformations for those amino acid residues when they are under biological conditions. Proteins in any of their functional folded conformations are called native proteins. So kanang dili siya, wala siya altered no, when we take out a fraction of or the proteins in their under biological conditions. We have their what you call that one is a native protein. So when you change the environment of that particular proteins from, for example, we have a sample of proteins under biological conditions. Like say, for example, the protein albumin sa egg. Now, if you place that albumin sa egg under in a different environment, let's say, for example, we put a little bit of acid, no? Kung kanang albumin, the albumin that we have from the egg, we put some acid or we stir it, we put some mechanical forces, no? That structure or conformation of the amino acids in the protein can actually be altered. But without that any alteration, adding any other reagents, no, we have the folded conformations of the proteins. We call that one in its functional form, no, where it can function like carries, for example, hemoglobin, where it carries blood. With native conformation, we call that one as the native proteins without adding any other reagents to it that could alter its stable, you call that one conformation. Okay, so first you have the primary structure, and we learned that one, we call it primary structure again. You have the sequence of the amino acids, no? Here is an example of human myoglobin. No, it's a protein. It's a globular, also protein part of it. You have this from the N terminus N to the C terminus N. You have, I hope maklaro, you have the glycine, leucine, serine, aspartame, glycine, glutamic acid, tryptophan, glutamine, and so on. Okay, there's a lot of sequence, and you have your cysteines. They're close to each other, actually in a close proximity, rather like 1, 2, 3, 4, 5, 6, in less than 10 amino acid residues. It's possible for cysteine to form a disulfide bond to form the cysteine with the TINE, no, a disulfide bond structure. Or when they are in close proximity with a different polypeptide structure, but they are in close proximity, it's also possible for cysteine to form a disulfide. Anyway, so this is what we call as the primary structure of the protein, where it shows on what are the primary sequence of the amino acid residues. And of course, we learned that one. Always when we do the sequence of the amino acid residues or the polypeptides, we always start from the N terminus and to the C terminus. And also when you write on the structure, you write in such a way that on the left side, so you don't get confused, the left side is your N terminus end, and on the right side of the structure is your carboxylic end. It's easy for you to form the hydrolysis and see how to remove the water, since in the formation of the peptide bond, it simply is a hydrolysis reaction. And in the secondary structure actually refers to the local conformation of some part of the polypeptide bond. No? The discussion of secondary structure most fully focuses on the common regular patterns of the polypeptide structure. So there is the common folding patterns of the polypeptide structures. The most prominent one is actually, we'll discuss later, is the alpha helix and the beta conformation. And when this amino acid sequence assume the secondary structure, for example, alpha helix or beta conformations, there are two most structural patterns that reflects the two simple pattern rules. First one is that the hydrophobic residues, katong hydrophobic ends sa imong amino acids, residues are largely buried in the protein interior. We have to remember that when these amino acids or the polypeptides actually is under biological conditions, our solvent is water. Okay, so the environment is water, usually at the pH 7 in that range. And when we have in the side chain of the amino acid, we have hydrophobic residues. They are largely buried in the protein interior, away from the water, since there will be no interaction that would come from. Those are hydrophobic. From the word hydrophobic, they are water bearing, right? So they will be buried inside the protein interior, and the number of hydrogen bonds within the protein is maximized. So those group of atoms in the amino acids that can form hydrogen bonds actually maximized, because that one can stabilize hydrogen bond formation in the protein structure, can actually stabilize the conformations of the protein. So the first structure of the secondary structure that we'll be talking is the alpha helix. The alpha helix is like a helix, that you can see. In the protein, we start from the N terminus end to the carboxy terminus end, or the amino terminus ends. From top, if we form a helix from top to bottom, it will be like a right-handed helix. Now, how it rotates, there is this helix form for a certain number of residues of protein, amino acid residues. The amino acid residues turns, it folds, like it turns, rotates. Now, if there is like an imaginary axis, and around that the protein falls. Again, you have to remember that the peptide bond, there is that CC bond in there that can be rotated around its axis, except for the C double bond O and CN. There is that NC bond that can also be rotated, and because of that, it's possible for your amino acid to form rotations. But it is not that can stabilize our alpha helix structure. The hydrogen bond forms between the NH group of amino acids and the carbonyl group of the amino acid for residues, stabilizes that and forms a bond, and that will actually stabilize the alpha helix structure. So where is that? Nadiri, So you have the NH group here, and there is this carbonyl group here, C double bond O group here. It would form a hydrogen bond, this one, C and H, CO and NH. It would form a hydrogen bond, and that 5.4 or 3.6 residues away, or 5.4 angstroms away, is the repeat unit of this structure alpha helix. So around 3.6 residues away from the last amino acid, then there is another rotation to form the alpha helix. And the rotation is a right hand helix rotation, alpha rotation. Right hand, no. So what is that right hand? When you look at your hand, you try to fold it. The direction of the rotation is pataas, no? Pana. Like this way. Because there is another helix rotation. So it's a right hand helix rotation. So pataas. Now the rotation is paana and then pataas, direction upwards here. So why does the helix form more readily than many other possible conformations? So there will be other conformations that the amino acid residues can actually conform to. But why would this alpha helix is very predominant in the protein structure? Number one is that the helix makes optimal use of internal hydrogen bonds. So there is a hydrogen bond that I have mentioned. That hydrogen bond stabilize the structure, the alpha helix is stabilized by the hydrogen bond between the hydrogen atom attached to the electronegative hydrogen nitrogen of the peptide and the electronegative carbonyl of the fourth amino acid of the terminal side of the peptide. You have in here. Okay. You have here. So you have the N C double bond O. Okay, you have here C double bond O, and you have the NH from the peptide bond. I hope naklaro siya diri. You have the NH and the C double bond O. So you have your 1, 2, 3, ika 4, no? Ika 4 nga amino acid. So you have the hydrogen bond. And this hydrogen bond in the helix, no, in the alpha helix, it stabilizes this helix structure. Okay, there is this kind of rotation here. You can rotate the NC bond. Okay, see this, there is a rotation. But what stabilizes this is not na in between here, katong pag-rotate, but somewhere here far, kaning dapit sa gawas, no, that would form a hydrogen bond, the C, the O, and the hydrogen connected to the N here, the amide bond, can actually form a hydrogen bond, and this one stabilizes the helix structure. So once again, it's suraan na, no? If you look at this, the helix, no, there is this hydrogen bond formation here, hydrogen bond formation here, and the hydrogen bond formations every 3.6 or approximately 4 amino acid residues away. So on 3.6, it's siya complete, but it is on the 4th amino acid, no, when the hydrogen bond forms. So you can see here you have 1, 2, 3, ika 4 gihapon. So it's complete, but like here 3.6, almost 4, but 3. But this amide comes from the 4th amino acid. So that's why 3.6 residues away. So you can count the first amino acid, second, third, there's a hydrogen bond. First amino acid, second, third, you have the 4th amino acid. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. So this is how the hydrogen bond in the alpha helix forms. Again, this alpha helix is stabilized by the hydrogen bond between the hydrogen of the amino acid and the C double bond O, the oxygen of the carbonyl oxygen. Carbonyl oxygen atom, the 4th amino acid. Okay, and so another Why would the helix form more readily than many other possible conformations? Second is that within the helix structure, every peptide bond, except those close to the end of the helix, participate in each hydrogen bonding. Each successive turn of the helix is held to adjacent turns by 3 to 4 hydrogen bonds. So this is what I have mentioned earlier, that each successive turn of the helix is held to adjacent turns by 3 to 4 hydrogen bonds. So there is the hydrogen bond. Listen, there is this hydrogen bond, there is this hydrogen bond here. But that repeating hydrogen bond actually is occur every 4 amino acid, or 3.6 in particular. Every 4 amino acids you can count. So there is a hydrogen bond here, makastabilize siya. There is this hydrogen bond. There is this hydrogen bond. 1, 2, 3. You have 4 here. There's also hydrogen bond here. So there's too much hydrogen bond and it really stabilizes the alpha helix. Okay. Once again, itong hydrogen bond, of course, is a hydrogen bond formation between an electronegative atom like oxygen bonded to hydrogen, wherein this hydrogen is bonded to an electronegative atom, nitrogen, or it can also be bonded to oxygen or fluorine. Those are the definition of our hydrogen bond, if you remember. Okay, so you have a hydrogen bond and it stabilizes the alpha helix. So if you look at the top structure, this is how it looks like. Now you have the R group, nasa gawas, it's oriented outwards, of the helix. And you have here the, like a hole here, for the alpha helix, and there is a turn every 4 amino acid residues away. And this is how the 3D structure is if you look at the helix of the amino acid. Amino acid chains are projected towards outside of the helix. So constraints rather that affects the stability of an helix is the electrostatic repulsions between successive amino acids with charged R group. If there is, for example, an amino acid here, kaning R, that are charged and they are of similar charge, it can destabilize the alpha helix. Now, it will disrupt naman. It will be, for example, let's say that you have an R here and you have an R here. If they're in close proximity and this R is charged, let's say passively charged and this is passively charged, then it will, they are in close proximity, they will be disrupted, because there will be so much repulsion that there won't be a possibility of hydrogen bond formation if there are some few distance farther because of the repulsion. So any electrostatic repulsion between successive amino acid residues with charged side chain, the R groups, can destabilize the alpha helix. Next one is there is an bulkiness, there is a bulky adjacent R groups. Okay, pag bulky siya, for example, very long, and then there is an aromatic R group, it's very bulky. And it can also destabilize the alpha helix or can affect the alpha helix. Third is if there is an interaction between the R groups spaced 3 to 4. If there is an interaction between R, here we just depict what are the R generally, but sometimes your R can be like very large. If there is an polar groups, or if it's hydrophobic, for example, so it doesn't want to be this exposed to the helix away. So it can also affect the stability of the helix. And then you have the occurrence of the proline and the glycine residues. The proline structure is katuna siyang aromatic, it's kind of bulky. And there is an aromatic, it's very short, and it's kind of bulky. And then you have the glycine, which is very, very short. It's just made up of, the R group is just made up of hydrogen. So that will affect those things, will affect the stability of the helix. As I mentioned again, the interaction between the R groups, any possible interactions. Now, unsa na mga interactions, you have to remember on your basic weak electromolecular force of interaction. Now, there are different intermolecular force of interaction. If you remember, you can have your hydrogen bond, you can have your ionic interactions. Remember, you have your van der Waals interaction. Of course, there's always a van der Waals interaction. The most strong one is you have the ion dipole interaction. Okay, if you see an ion in the structure of the polar organic moieties, you have that, or organic side chains, and then close proximity to the ions. If you remember your general chemistry, you have these different interactions. I think we have already mentioned it. You can also have hydrophobic interactions. What else? Of course, polar dipole interactions, when polar groups, when you have your polar groups, when you have, for example, katong mga electronegative atoms, no, but not necessarily connected or having a hydrogen connected to a polar group of atoms. So are your polar group of atoms, katong na yung mga oxygen, nitrogen, no, those are, you can readily know that this group of atoms can be polar by virtue of the electronegativity of those atoms. No? So kato, you have to remember that in your general chemistry. The interaction between amino acid residues at the end of the helical segment and the electric typo inherent to the helix. So this can also affect on the stability of the helix. It's already been mentioned that the R group spaced 3 to 4 residues away can interact, may have an interaction, no? So it can affect the stability. It may stabilize more, or it could stabilize, destabilize rather. It can stabilize or it could destabilize. Okay, for example, they are both hydrophobic, close sila in proximity, so ganahan sila because there will be some kind of hydrophobic interaction or weak, more of that weak van der Waals interaction. If polar and non-polar groups are close to each other, R groups, polar R groups and non-polar R groups are close to each other, so there will be no interaction, of course, and it could affect the stability of the helix. Okay. So the more on that, the interaction between amino acid residues at the end of the helical segment. So what are that ones? Kanina sa end, no? The amino acid residues, interaction between amino acid residues, I have already mentioned. In particular, kanina sa gawas, kanina sa kilid, no? It can also affect whether it will stabilize or destabilize the alpha helix. If it destabilizes the alpha helix, actually, it will disrupt on the alpha helix structure. For example, if this R, again, I have already mentioned, this RR has no point of interaction but destabilize this one, then it will disrupt the hydrogen bond and probably another secondary structure will be formed other than the alpha helix. So in general, the tendency of a given segment of a polypeptide chain to fold up to a helix structure therefore depends on the identity on the